Okay, hi class. So now let's understand how a transformer works theoretically. Now I've got an AC source. Okay, so assuming that this part AC, this is plus, this is minus, and it sends the current down here and into the circuit and comes out. From this perspective, because my electromagnet is this here in this orientation, I look at it from this perspective. And when I look at it from that perspective, my current goes in like that, which is anti-clockwise in my perspective, and hence the north is formed and the south is formed at the bottom of the transformer. Now what this does is, because I've got this iron sheet to concentrate the B field, all the B field is going to be concentrated inside this laminar. So basically I will have B field going around. I'm going to go inside the laminar, and this is how it's going to go. So I've got B fields going from north to south inside the laminar. Now, there will not be B field going out of the laminar sheet. So this is theoretically not possible. Anything out is not possible. It's going to be wrong. Okay. Now, because this north field connects it to this coil, so I got a wire cutting the B field. So I will have, according to Faraday's law, a pole here is like the north going very fast approaching this coil. And if the north here approaches here there will be induced north, like taught to you before. You will reject it, Faraday's law. So because of this north, then this will be north, induced to reject that. At the same time, this south, and then to repel this, then this side has to be induced south. Okay. Now what this does is that it creates a current. Okay. So the current on this side, because it's north, it has to be anti-clockwise current direction, like taught to you before. North is anti-clockwise current direction. So from this perspective, anti-clockwise means it goes in this direction. So if it goes in this direction, okay, it comes out, okay, it goes, so it must be in this direction. Clockwise. Anti-clock. North is anti-clock. So it goes in this direction. So it goes in, and hence in this direction, and it comes out. But this is induced current. The current is induced. It wasn't there before. It was induced. This current was induced. So I've got this current that moves in this direction. So this current is now secondary. Okay? And again, this is AC. Okay? The secondary current is also AC. Okay? So, but after a while, this plus and minus will switch because alternating current switches current. So, this will now be switched. The polarity will be changed. So, this will now become minus and this is going to become plus. Now, there's a problem because this magnetic field of north and south, this pole, was there. But it will now have to collapse. It has to diminish by this new pole here, the new terminal that will destroy the existing order. So, this north will slowly and be destroyed. This becomes south and this becomes north. Now, while this is changing on the left side, the right side has a response. This north is dying. Okay, so to attract this north, okay, this guy has to form a south. Okay, so this north is dying and south is forming. At the same time, it triggers the change on the right side, so that this side now becomes an induced south to repel the south, the new south, and attract back the old north. At the same time, this north has this induced pole here has to repel the north and attract the south back, and hence this is an induced north form. This is the newer magnetic pole forms at a later stage. Because of this, the current here has to change. So it flips around again. So instead of going this direction, now the new current will go this direction. See, there's a flip. Okay, so there's a flip. And therefore, an AC current, okay, at the secondary side is formed. Okay, that's how you do it. Now, in the real world, okay, it may seem like as if I'm taking an AC source on the left-hand side to produce an AC source on the right. Is that how we produce electricity? No, that isn't it. Although here is AC on the left, it's really reproduced from burning of the mass of trees that we have, or running turbines in water where the water purposefully go through some turbines. And when it does that, okay, it turns the generator that you learn. So let's say, for example, if I have got a generator underneath a water reservoir. So it's going to look like that. So I have a huge amount of water here. So I channel at the bottom there's high pressure, right? So I channel the water into a turbine, and it turns the blade, something like your AC generator for and it turns the turbine. Okay. So remember the armature in the generator, as it turns, it generates electricity. So as it turns here, it generates electricity. This part here is this part. This part. So this electricity is fed off this portion of the turbine that's placed at the bottom of the water reservoir. Okay, that's how you multiply the electricity from the primary side through coil ratio, okay, that we have in a transformer, and you multiply that 10 times, 20 times, 30 times higher than normal. So that's how we multiply voltages, and that's the right side you then supply to household electricity and all that. That's the beginning of consumer electronics and consumer electricity. Okay, I hope that answers a whole lot of questions about how we get electricity to the household nowadays. Thank you very much.